Alrighty, so domain from a function. I'm going to start by asking you to find some y-intercepts. This is something that we did back in our first unit, find the y-intercept if I have a function. Does anybody remember what we did to find the y-intercept from a function? What could I do here? What's the y-intercept? If I ask about the y-intercept, what am I asking you for? On a graph. Where the graph? Mm-hmm. Yeah, when I hit the y-axis when x is 0. So we want to plug in x equals 0 here. I would like you to do that for me now. Plug in x equals 0 for our three functions here. Give me the y-intercept if it exists. In our first function, quadratic function, because I've got x squared here. If I plug in 0 for x, I would have 2 times -3 squared plus 4. Make sure you're following order of operations inside parentheses first. Then we square. So -3 squared would be 9. Then we'll multiply. 2 times 9 is 18. And then we add. So 22. My y-intercept will be 22 here. For g of x, I have an exponential function. We saw these back in Algebra 1. We saw quadratic functions in Algebra 1 as well. So 3 to the x. We're plugging in 0 for x. That would be 3 to the 0. What do I get if I take 3 to the 0? Just 1. Anything to the 0 power is 1. So I have a y-intercept at 1 there. And then for h of x, we're plugging in 0 for x. That would be the square root of 0 minus 2. So if I simplify under the root, that'd be the square root of -2. And then I've got to stop there. Why do I have to stop there? Can you tell me the square root of -2? No, right? We can't take the square root of something negative. That is a non-real value. It's undefined in the real numbers. So this guy has no y-intercept. We're going to talk about domain from a function for today. And what we're going to be on the lookout is for are things like this: square roots of negative numbers, things that are undefined. Remember, we also saw some functions like this, where if I plugged in 0 for x, I would get something undefined. I'm going to be on the lookout for values of x that would make my function non-real, so a negative under a root, or undefined, like when I divide by 0. Okay, that's what we're going to be on the lookout for today. As we're talking about our functions, I grouped them into function families, function types. The first type that we're going to see are polynomial functions. Polynomial functions we have seen before. In Algebra 1, we spent a lot of time talking about linear functions and quadratic functions. They belong to the same family. They have the same characteristics. They behave the same way. This also includes x cubed functions or x to the 4th functions called cubic or quartic functions. If I had x to the 5th, x to the 6th, x to the 10th, x to the 17th, I can have multiple x's with different exponents sort of sprinkled in there. Those are all what we call polynomial functions. My variable has a positive integer exponent. That's a polynomial, okay? X has an exponent that is a positive whole number. That's a polynomial function. And again, we can group them together because they all kind of behave the same way. So I want to talk about the domain of polynomial functions. What we're going to be on the lookout for are any values for x that give us something not real or undefined. Well, as I take a look at my polynomial functions, do you see division in any of these? Like, do you see division like this in any of these, for example, 1? No, no division, right? So I know right out of the gate, we're not going to have anything undefined because we're not dividing by anything. So I can't divide by 0 if we're not dividing. Do I see any square roots here in any of these problems? Any square roots? No, no square roots. So I know I'm also not going to have to worry about square roots of negative numbers because we don't have any square roots. So what we're going to look at are some sort of like big categories of values. Okay. Can I plug in positive numbers for x? Can I plug in negative numbers? Can I plug in 0? Could I plug in fractions? That's what we're going to ask ourselves and kind of look to see if I have any problems. So for my first function, a quadratic function here, an x squared function, we talked about those back in Algebra 1. Could I plug in a positive number for x? Would that be okay? If I plugged in, let's say 2 for x, would that be an okay thing to do? Like, could I do 3 times 2 squared plus 5? Is that okay? Yeah, that's okay. I would get 3 times 4 plus 5, so 12, 17. That's okay. Could I plug in like 7 for x? Would that be okay? Sure, I'm not going to get anything that's not real. I'm not going to get the square root of a negative. I'm not going to be dividing by 0. I can plug in any positive number that I want. What about negative numbers? Could I plug in, for example, negative 2? Would that be okay? Sure. Yeah, I would still get 17, right? Negative 2 squared is 4. Times 3 is 12. Plus 5 is 17. Could I plug in negative 7 or negative 100? Sure. No problems there. Could I plug in 0? Could I let x be 0? Would that be okay? Sure. Yeah, x could be 0. That's okay. That would give me the y-intercept, right? That's an okay thing to do. Could I use a fraction? Could I plug in a half for x? Sure. I mean, do I want to plug in a half for x? Probably not. But could I? Yeah. I'm not going to get anything undefined. I'm not going to get anything that's non-real. I can plug in any value that I want for x. Okay? Anything I want. That means that my domain is what we call all real numbers. Anything from negative infinity to positive infinity. If you like the inequality notation, that would look like this. All real numbers here. Negative infinity to positive infinity, anything you want. X can be anything. For B, we're going to ask ourselves the same questions. B is a linear function this time. My exponent for x would just be 1. That's a linear function. Could I plug in positive numbers for x? Sure. Could I plug in 0? Would that be okay? Yeah. Could I plug in a negative number? Sure. Could I plug in a fraction? Sure. I mean, I probably don't want to, but could I? Yeah. Remember that linear functions are lines, right? It looks like this. It's going to be a line with a slope of a half. And so if I think about this on the coordinate plane, right? Wherever that lands. If I think about this on the coordinate plane, it's going to keep going forever this direction. So any positive x value is okay. I could have a y-intercept, so 0 is okay. It's going to keep going forever this way. Any negative x value is also okay. So this would be a domain of all real numbers. If I were to think about my quadratic function, same idea. This is going to be a flipped upside down quadratic. But any quadratic, even if I thought about my parent function quadratic, we're going to go forever this way, forever forward, right? Forward and up, forward and up. So I'll have all those positive values that I can plug in. Same on the other side, all those negative values too. Even if I'm talking about a parabola that's flipped upside down, we're going to go forever this way. We're going to go forever this way. So I get all the positive x's and all the negative x's and 0. Fractions are okay. We get all the values back. Everything's fair game. C is what we call a cubic function. If I were to distribute this out, I would have x cubed, 3 as my greatest exponent. Right? Since we're talking about these polynomials as families, really quickly, this would look something like this. Trust me on that for today. I know we haven't talked about the graphs of cubic functions yet. We will later on. For today, just trust me that that graph will look something like this, okay? I'm going to have positive x values as far as I want, negative x values as far as I want. I could plug in 0 here, that'd be okay. I could have fractions. I probably wouldn't really like to plug in fractions, but I could plug in fractions for x. My domain here would be, again, all real numbers. I can plug in anything that I want for x, anything at all. Are you seeing a theme with our polynomials? What do you think the domain will be for t? Same thing, right? All polynomials have a domain of negative infinity to positive infinity, all real numbers. We can plug in anything we want. Positives, negatives, 0, fractions, decimals, anything we want. All real numbers. So that question at the bottom asks us, are there any values that we can plug in for x that would give us something that's not real or something undefined? No, there's nothing that we could plug in for x that would make this function not real or undefined for any polynomial. No, there are no values. So all polynomials have a domain of negative infinity to positive infinity, all real numbers. Why we can talk about them together as a big group. The next function family we're going to talk about are exponential functions. We saw an exponential function in one of our warm-up problems, 3 to the x. When we talk about exponential functions, we are talking about functions where the variable lives in the exponent. We have a positive base for the exponent. It's some positive rational number. It could be a whole number, like 3 or 4. It could be a fraction, like a half. But it is some positive numerical base raised to an exponent, and the exponent has the variable. X lives in the exponent. So 3 to the x, 2 times a half to the x plus 1. I can have other stuff in there too. The important thing is that x is the exponent, and our base is a positive number, a positive number. So let's take a minute to make a little table here and kind of talk about what we can see. So if this is my function here, and I'm going to plug in these different values for x, this would be 10 times 2 to the negative 1. Can I have negative exponents? Should be getting big nods. Yes, that was on our last test. Yes, we sure can. What does a negative exponent do? Flips it, right? Takes the reciprocal. This would be 10 times 1 over 2 to the first, which would be 10 times a half. Half of 10 is 5. If I plug in 0 for x, this would be 10 times 2 to the 0. Can I have 0 as the exponent? Sure, we did it, I don't know, 5-10 minutes ago with that warm-up problem. What's 2 to the 0 power? 1. So this would be 10 times 1, which is 10. And then I have a positive number for my exponent. 10 times 2 to the 4th. So that would be 10 times 16, which is 160. So we did negatives, we did 0, we did positive. Could I do a fraction? Like, could I do a half? 10 times 2 to the half. Remember that fraction exponent we can represent as a root. So this would be 10 times the square root of 2. Do we know what the square root of 2 is? It's not a nice number, right? So I'm just going to leave this as 10 times the square root of 2. Whatever that number is, it's going to be some decimal, right? But I could do fractions. That's okay. Are there any values I could plug in to my exponential function that would give me something not real or undefined? No, we can plug in anything we want. Exponential functions also have a domain of all real numbers, anything from negative infinity to positive infinity. We can use any value we want. The domain is all real numbers for exponential functions. So as we look at our example problems down at the bottom, exponential function 4 to the x, its domain, negative infinity to positive infinity, all real numbers. A little bit more complicated here. I multiply by something in front. I've got something else in the exponent. It's still an exponential function. Its domain is still all real numbers, negative infinity to positive infinity. For C, this time the base for our exponent is a half. That's okay. Our domain is still all real numbers, negative infinity to positive infinity. For D, we're subtracting something at the end. That's okay. Our domain values that it is okay to use for X, still all real numbers. So we've talked about polynomials and exponential functions. They both have a domain of all real numbers, negative infinity to positive infinity, whichever notation you prefer. I've used both here. Next, we're going to talk about square root functions. Based on our little warm-up recall problem at the beginning, we should already be a little bit on edge with square root functions. Okay? We know we can see some problems when we have square root functions. A square root function is any function where the variable is under the root. We call that the radicand. The part that's under the square root is called the radicand. Okay? So square root of x would be our parent function. 3 times the square root of x plus 2. Negative 1/2 times the square root of x minus 5. Then plus 2. These are all square root functions because x is under the root. If the variable is under the root, it is a square root function. So let's make a little table here as well. We've got some values to plug in for x. This would be the square root of negative 2 times negative 2. So that's the square root of 4. Any problems with the square root of 4? Do we know the square root of 4? What's the square root of 4? 2, thank you. Had me worried there for a minute. Let's plug in 0. Square root of negative 2 times 0. That would be the square root of 0. Simplify under your root first. Can I take the square root of 0? Yeah, it's just 0. Square root of 0 is fine. Square root of 0 is 0. And then if I plug in 4, this would be negative 2 times 4. That's the square root of negative 8. Can I take the square root of negative 8? No, this is not real. We get something non-real, or some of you in our earlier unit told me undefined because the square root of negative 8 is not defined in real numbers. Okay, so we need to be on the lookout for anything that would make our radicand negative, anything that makes the stuff under the square root negative. I don't have one big rule, one domain that works for every square root function, like we did for exponentials and polynomials. It's going to vary problem by problem, function by function, because every square root function is a little bit different. But the big thing that we can say, okay, we have to look out for stuff that's going to be non-real. So we're looking at the radicand. Okay, which is the stuff under the square root. The stuff under the square root must be greater than or equal to 0. It's okay if it's 0. We can take the square root of 0, but it can't be negative. 0 is as low as we can go. It's got to be greater than or equal to 0. So for our square root functions, we've got to go case by case. What would make the radicand 0? So for A here, here's the radicand, the stuff under the square root. that needs to be greater than or equal to 0. So I'm just going to set it greater than or equal to 0 and then find x, solve for x. Remember, when we're solving inequalities, it works just like an equation unless I multiply or divide by a negative number. Does anybody remember what we have to do if we multiply or divide by a negative number? What happens to my sign? It flips the other way. For this guy, we're just subtracting, so I don't need to do anything wild. So x needs to be greater than or equal to -3 here. You should be able to go back and double check and make sure that this makes sense. If I plug in -3, that would give me the square root of 0. Is that okay? Is it okay to do the square root of 0? Yeah, we could do the square root of 0, right? We did the square root of 0 up here. That's okay. This says it could be any number bigger than -3. So let's say I plugged in, I don't know, 1. That's bigger than -3. That'd be the square root of 4. Is that okay? Square root of 4? Sure. Even if I picked a number that didn't have a nice square root, as long as it's positive, that's okay. What if I pick something less than -3? What if I did the square root of -4? That'd be the square root of -1. Is that okay? No, that's the problem. Okay, so never a bad idea to go back and double check what you got. Our domain then needs to be all values of x that are greater than or equal to -3. This is okay to give me as your domain. If you like the inequality that's got 3 pieces to it, it would look like this. -3 is less than or equal to x is less than infinity. Or if you like interval notation, anything greater than or equal to -3 would look like that. Bracket at -3 because I can have -3 as a value. It's okay. -3 or bigger, -3 to infinity. B has a rational exponent. The exponent's a fraction. We need to be careful when we have rational exponents because I need to pay close attention to that denominator. This guy, I could rewrite as 2 times the square root of x cubed. Since 2 is in the bottom, it's a square root. That means I need to make sure that the radicand, whatever's under the root, is greater than or equal to 0. In this case, I don't need to do any solving. X is already by itself. So I'm looking for x values that are greater than or equal to 0. 0 would be okay to plug in. We can take the square root of 0. Nothing negative. All positive numbers would work. Anything positive would be okay. So again, you can leave it like this. If you like that 3-piece inequality, it would look like this. Or interval notation, 0 to infinity with a bracket at 0 because we can use 0. 0 is okay. And then same idea for C and D. I need the stuff under the root, the radicand, to be greater than or equal to 0. So x minus 1 is greater than or equal to 0. And we get x by itself. So x is greater than or equal to 1. That should make sense, right? The lowest number I can have under the root is 0. I can take the square root of 0, but nothing negative. If I were to use 1, if I plug in 1 for x, that would be the square root of 0. So that's our boundary. Anything bigger is okay, not anything smaller. In interval notation, this would be 1 to infinity. For D, the radicand, 3 minus x, must be greater than or equal to 0. Let's get x by itself. We'll move that 3 to the other side. Be careful with your signs. And then I've got to divide by -1. I don't want negative x, I want just x. Since I'm dividing by a negative, my sign flips. X must be less than or equal to 3. if I were to plug in 3, that would be 3 minus 3, which is the square root of 0. So 3 is okay, but this is telling me you have to be less than 3. If I plug in a number bigger than 3, let's say I plug in 4, that would be the square root of a negative now. Less than 3, numbers like 0 or even negative numbers would be okay. Since we're subtracting x, if I plug in a negative, we would add. So those would be okay. So this guy's not, but everything else is good. So x values less than or equal to 3. If you like, again, that 3-part inequality, this would be negative infinity is less than x is less than or equal to 3. Interval notation would be negative infinity up to 3, always a parenthesis at infinity, and a bracket at 3. So for square roots, we have to look at the individual function. I don't have one big rule for all of them. The last type of function we're going to talk about today is another one where we're going to have to look at the individual function. So on the next page, page 16 for me, we're going to talk about log functions. Log was a new one that we got this year. We know that they're related to our exponential functions. And when we talk about logarithmic functions, when we talk about log functions, we're talking about x, the variable, being in the argument of the log. Okay, when I'm referring to a log function, I mean that the variable is in the argument of the log. Okay, and this guy right here, what I'm taking the log of is the argument. So they're all log functions. And we're going to start again with a table for our log function as well. Remember that logs we can rewrite in an exponential form. And for me personally, that's a little bit easier way to talk about these. So this would be 2 to the something, which will be our y, equals 4 minus x. Be careful with these. The biggest issue we had with log functions in our last unit was we forgot that x was not the exponent. X is not our exponent here. X is over here. This is not x, this is x. So if I'm plugging in values for x, I need to be careful about where I'm putting those numbers. So this would be 2 to what power is 4 minus negative 12. Minus a negative, I would add there. And 4 plus 12 is 16. 2 to what power would give me 16? 2 to the 4th, very good. And then 2 to what power would give me 4 minus 0? 4 minus 0 is 4. So 2 to what power would give me 4? 2 to the 2nd power. 2 to what power would give me 4 minus 3? We're plugging in 3 for x. 4 minus 3 is 1. 2 to what power would give me 1? 0, yeah. 0 power always gives me 1. 3.5, we're going to plug in 3.5 for x. The 2 to what power gives me 4 minus 3.5. 4 minus 3.5 would be a half. 2 to what power would give me a half? Negative 1. Yeah, we saw those negative exponents in an earlier example. I can get a fraction if I flip, right? Take the reciprocal. That's a negative exponent. 2 to what power would give me 4 minus 4? 4 minus 4 is 0. 2 to what power would give me 0? Nothing, right? That's a problem. I can have 0 as an exponent. 0 as an exponent is okay. We saw that when we plugged in 3, right? I can have negative numbers as exponents. That's okay. But there's no power of 2 that's going to give me 0. Multiply 2 by itself a bunch of times, you're not going to get 0, no matter how many times. Take a root of 2 a bunch of times, you're not going to get 0. Take the reciprocal of 2, you're not going to get 0. This is undefined. I can't have 0. And then our last one here, we're going to plug in 8 for x. So 2 to what power gives me 4 minus 8? 4 minus 8 would be negative 4. 2 to what power would give me negative 4? Anybody kind of want to tell me negative 2? Not even a little bit? It's not negative 2, right? Negative 2 tells me take the reciprocal. Negative exponent tells me reciprocal. Okay? How many times can I multiply a positive number by itself and get something negative? It's not going to work, right? I can't take a bunch of positive numbers and multiply to get something negative. This is also undefined. So for logs, again, there's not going to be one rule that fits every log function. Instead, what we're going to have to look at are excluding any values from the domain that would take 0 or a negative value in the argument. Okay? So the argument must be greater than 0. Whatever I'm taking the log of must be greater than 0. So this part, greater than 0. Again, this is going to be case by case because I can have other stuff besides just x in the argument. We've got to look at case by case. What would that domain be? So for A, the argument must be greater than 0. My argument this time is just x. It must be greater than 0. I don't have any work to do to get x by itself there. So that's my argument. X is greater than 0. In interval notation, 0 to infinity. And we're using parentheses this time because I cannot have 0 as the argument. It's got to be greater than 0. For B, x minus 2 must be greater than 0. The argument must be greater than 0. Get x by itself. And my x values must be greater than 2. If I plugged in 2 here, I would get 0. So it's going to be something bigger than 2. In interval notation, this would be 2 to infinity, parentheses on each side. If I can't use 2, that would get me 0. It's got to be bigger than 2. Try C and D. For C, the argument has to be bigger than 0. You do have a little work to solve for x here. You get x must be greater than negative 4. This is fine. If you like the 3-piece inequality notation, this would be negative 4 is less than x is less than infinity. Or in interval notation, negative 4 to infinity, parentheses on each side. And for D, our argument is just x, so x needs to be greater than 0. 0 to infinity is interval notation, parentheses on both sides. Or 0 is less than x is less than infinity. Questions for me on those? Okay, so we talked about polynomials, we talked about exponential functions, we talked about square root functions, and we talked about log functions. We're going to talk about something called rational functions next. Those are where I've got something with x on the bottom of a fraction. We're going to talk about those. We're going to take a couple days to work on those coming up next. For homework, I would like you please to work on pages 17 and 18. If you remember the domains for